This lesson is on combinations, but more advanced questions, or at least variations of the questions that we were looking at in the previous lesson. A lot more algebra as well, you'll see. Now to start off, question that we saw variations of yesterday, how many 5-card hands contain at least one red card? Now the only thing that's troublesome about this question is the fact that the phrase at least, or the words at least, are referred to. At least suggests that you have more than one possibility, and it means that we're going to have to add. It means the word or is implied. And that can be a lot of work, although very manageable as long as you recognize it. So I would begin by indicating all the possibilities we have. This really is a mixed committee, because we could have 1 red and 4 black cards. That would satisfy the condition. At least one would mean we could have 1 red or more. So the other possibility, or the next possibility, is 2 red, 3 black, or 3 red, 2 black, or 4 red, 1 black, or 5 red, 0 black. These are the possibilities. Now this is a lot. We could add them all together and work it out. So I would advise you to think about an indirect solution instead. And an indirect solution, remember, means that you look at the total number with no restrictions, and then you subtract away the ones you don't want. So for this question, the total number of ways to arrange these 5 cards with no restrictions, red, black, or anything, would be 52. Choose 5. And the ones that we do not want, there's only one possibility. We don't want 0 red, 5 black, all black. That's what we cannot have. So we work out the number of ways that that could be formed, 0 red, 5 black, and then we subtract it. And that would be 26 choose 0 for the red, and then 26 choose 5 for the black. Now 26 choose 0 is just equal to 1, so you don't even need to include that if you don't want, but no harm will come if you do. And then when you work this out and subtract, you'll get a big number still, 2,533,180 card hands. But it was way better than adding them all together. So you should be asking yourself, for any question where you're adding a bunch together, ask, is there an easier way? Would it be easier for me to do a subtraction, an indirect method for it? Next question, kind of an interesting one. 8 people volunteer to help out at a bake sale. 3 are needed to sell muffins, 2 are needed to sell cookies, and 3 are needed for security. In how many ways can the volunteers be arranged? Well, this starts off as a nice combination question. You have to figure, well, these 3 people that are selling muffins, the question does not give any information suggesting that there's any sort of particular distinctions amongst the muffin sellers or the cookie sellers or security. So it is a combination. So you start off with these 8 people that are in front of you, if you like, and you're going to assign them to their tasks. Now for the muffin sellers, so using combinations, we would find those 3 people. Then we would go on to the cookie sellers and assign 2 of them to cookies, and then the 3 remaining people would then be assigned to security. In any order, really, it wouldn't make any difference. So for the muffin sellers, we've got 8 people in front of us. We choose 3 of them. 8 choose 3. The cookie sellers, there's only 5 people left, and we will choose 2 of them. And then the security would be 3 choose 3, so just the remaining 3 people. And important that we are multiplying. This is not an or question. We're not assigning, finding muffin sellers or cookie sellers or security. It's and. So the word and is implied, if not outright stated. And that tells us we multiply. And then you just put it into your calculator, and you should get 560 ways. Now, that's a very common way to do the question. Another way would take us back to identical objects that we were doing a few lessons ago. It may have occurred to you, in a case like this, that if you assigned a letter M, say the letter M, to muffin sellers, and the letter C to cookie sellers, and then the letter S for security people, then this is what you have, these 8 letters, and you arrange them as though they're identical objects, because that's all that you're doing. So that would be the total number of letters, 8 factorial, divided by 3 factorial for the M's, 2 factorial for the C's, and 3 factorial for the S's. And that would then also give you 560 ways. So it's a legitimate way to solve the question. Depends on what you saw. My experience is that most people do the combinations, but it really doesn't matter. Another sort of specialty question. There are 20 teams in a baseball league. How many games will be played if each team plays each other team 3 times? Now, it is possible to solve this question in an Armstrong method. This is a variation of like what they used to call the handshake question, where you have a room full of people and you go around and shake everybody else's hand. So you shake all the other, say, 19 people. Then the next guy goes and shakes everybody else's hand, but not yours, because he's already shaken your hand when you were making the rounds. And then the following person would go around, shake 17 hands and 16, and then you'd add them all together. This is really the same thing, because you take a baseball team. This team plays everybody else 3 times, actually. And then the next team goes around and plays the remaining teams. But the thing of it is really a combination, if you think about it. Because all you're really doing is forming a little group of 2. Little group, or if you like the word, a little committee of 2. And order does not matter. Now some of you might be thinking, well, what about home teams or away teams and that sort of thing? Well, in terms of the number of games, it doesn't make any difference. You playing the Mets is the same as the Mets playing you. It counts as a game. So this leads us to an easier solution. 20 choose 2 would be the number of little committees of 2 that you can form, given that you have 20 to select from. And the fact that you play each other 3 times just means that you multiply by 3. And then that would give you 570 games. So that's the method for it that you want to be clear on when you encounter that. If you try to fumble your way through it, you might get the answer, but you'd probably invest a bit more time than you need. Now, polygons are a special case of their own. Some people cover these, some people do not. You really do need to know the method. I call it polygons, but really it's about diagonals of polygons. So for this question, we have a hexagon, so 6 sides, and we want to work out the number of diagonals that can be formed. Again, an Armstrong method would work, but you do run into problems with this. Now, the simple way to approach it, of course, is that you're connecting vertices, and you're therefore forming a little committee of 2. But it gets messy. Now, I'm going to start in this corner, and I'm going to work out a few of them. Not all of them. It just gets to be too much. There's one diagonal. There's another diagonal. And then there's another diagonal. And then I move on to the next corner. That one. That one. And then I fill in the rest of them because it's just too much work, too much bother to count them off all like that. There are too many to count by hand, at least comfortably. And it's easy to get mixed up. Because you see what's interesting about this question is if you are starting, say, from there, you never connect to the neighbor. You always just go to the opposing ones. And then it works fine for a while because this guy connects there, there, and there. But once you get to this one, you see that, okay, these 2 are new, but we've already counted this one. So as you work your way around, it's not just a matter of connecting to all the others because some of them have already had their turn. So the way we do it is with combinations, by thinking again that we're just forming a little group, a little combination of 2. And order doesn't matter. You connecting this one to this one is no different than you going the other direction. So the formula goes like this. N choose 2 minus n for an n-sided polygon. So you always subtract away the number of sides. And if you go back to that previous question then, you would get n choose 2 minus 6. And if you drive that through your calculator, you will get 9 diagonals. Another question, and this leads us more into the algebra end of things. There are 45 ways of selecting a committee of 2 students from an n-member class. So we have the answer. We know there's 45 ways, and we want to find the value of n. So it goes like this. N choose 2 is equal to 45. Now some of you would just fumble your way through and try numbers for n that work, and you'll get the answer right. So that's a legitimate way to solve it, particularly test question multiple choice. But if you did this the long method, recall that n choose r is equal to n factorial over n minus r factorial times r factorial. So we have that expansion that is available to you, and that leads us to this. N factorial over n minus 2 factorial. 2 factorial is 45. That n factorial and the n minus 2 factorial can be expanded like this. Remember, you expand the big one until it's equal to the little one, and then your n minus 2's go away. The other thing to be aware of is that when you have a number like 2, 2 factorial is just equal to 2. 2 times 1. So if you have number factorials, you can simply evaluate them. So this would mean that we get n times n minus 1 over 2 is equal to 45. So no more factorials. If you multiply both sides by 2, you'll get, and then distribute the n in, you'll get n squared minus n minus 90 is 0. Factor that into n minus 10 times n plus 9 is 0. And I'll bring up a new screen because our answers are right there in front of us now. N is equal to 10, n is equal to negative 9. Well, we have to reject the negative. You cannot have a class of negative 9 people, so we reject n equal negative 9. And then if n is equal to 10. So the class will have 10 members. Another algebra type question. We did these ones before back in pick. N choose 2 is equal to n pick 3 over 3 factorial. This is kind of an awkward looking one, although it does work nicely. And I'll do this one by hand. N choose 2, as we've seen, is equal to n factorial over n minus 2 factorial times 2 factorial. Don't forget, or if you do forget, look it up. N pick r is equal to n factorial over n minus r factorial. So n pick 3 becomes n factorial over n minus 3 factorial. And then this is all over 3 factorial. Now that 2 factorial and the 3 factorial can be cleaned up at any point. Now the difficulty with this one in my mind is that we have these complex fractions on the right. So you have a couple ways you can deal with it. I'm going to do it the conventional way, which I'll take that n factorial over n minus 3 factorial, and I'll remind you all that when you're dividing by 3 factorial, you're actually multiplying by the reciprocal, so that's 1 over 3 factorial. So this can be written as n factorial over n minus 2 factorial times 2 factorial is equal to n factorial over n minus 3 factorial multiplied by 3 factorial. So now we don't have that complex fraction anymore. And my advice would be to clean up these fractions. And you have a couple choices. And you could certainly simplify this a number of ways. You could multiply out the n by the denominators at this point if you wanted, or you could simplify the factorials first and then deal with some of the issues. It really doesn't matter. What I'm going to do is I'm going to multiply, just to do things a little bit fancy, I'm going to multiply everybody by, not by n minus 2 times n minus 3, but rather I'm going to multiply both sides by n minus 2 factorial times 3 factorial. And this might puzzle you a little bit because you're thinking, well, how is that going to cancel out my n minus 3 factorial and my 2 factorial? So this is a bit of a risky one, but let's see what happens with it. So we multiply the left side by that factor, and then there's no problem with n minus 2 factorial. It cancels. So we get n factorial, which remains. The n minus 2 factorial is canceled. And we could write this as 3 factorial, if you like, and then over top of 2 factorial, because you're thinking, well, did this actually cancel it out? Well, let's see what happens. And then on the other side, our n factorial stays where it is, and then when we multiply by n minus 2 factorial, I'm just going to keep it there temporarily, and then the 3 factorial cancels. So you're thinking, well, hang on a sec, we didn't cancel everybody. But in fact we did, and we could have done this more directly, because this n factorial, if we take that 3 factorial over the 2 factorial, you might be aware that 3 factorial is equal to 3 times 2 factorial. And then that's all over 2 factorial. And therefore, we're going to get rid of that 2 factorial. Just like this one, that n minus 2 factorial is equal to n minus 2. The next term would be n minus 3, because we're going down by 1. And then we stop right there. And then you can see that we will in fact cancel that denominator, and you could have done so immediately if you saw it. So these will go away, and we now get a very interesting situation. N factorial on the left, 3n factorial, because there's a 3 there, is equal to n factorial multiplied by n minus 2 factorial. And if you were to divide both sides by n factorial now, oh, by the way, that's not n minus 2 factorial, just n minus 2, which is good. The n factorials will go away, so we get 3 is equal to n minus 2, so n is equal to 5. So it does work. And I'm going to sneak the verification up in the top corner, a little bit tight up here. But if you get 5, choose 2. If you see if that's equal to 5, pick 3 divided by 3 factorial. So you just key them into your calculator and verify. So this is 10. And on the right side, 5 pick 3 is equal to 60. 3 factorial is 6. So we do get 10 equal to 10. So it did work out. Now with the algebra, you have to practice because you had lots of choices throughout this. Some of you might have simplified that n factorial over the choose and the pick first before you cleared the denominators, and you could have done that. Some of you might have multiplied by a common denominator of n minus 2 factorial, n minus 3 factorial, 2 factorial, 3 factorial, and it still works. You have to make different choices along the way. I did this one more to show you a different method because in some respects it's not the most obvious one. Let's do one more question and then that should get us through. Polygon has 44 diagonals. How many sides to this diagonal? So this forces us to use what we know about diagonals, which is that the number of diagonals is n choose 2 minus n, and that will be equal to 44. And then through our simplification, this becomes n factorial over n minus 2 factorial times 2 factorial minus n is equal to 44. If we simplify the factorial on the left, this becomes n factorial, times n minus 1, and then n minus 2 factorial. Expand until we can cancel. That's over n minus 2 factorial times 2 factorial minus n is equal to 44. we get n times n minus 1 over 2 minus n is equal to 44. And the only thing that's different about this question compared to earlier ones is the fact that we have that n term around. Now we multiply everything by 2, so we get n times n minus 1 minus 2n is equal to 88. And then we're in business. We can clean up this polynomial. N squared minus n minus 2n is equal to 88, which leads us to n squared minus 3n minus 88 equals 0. And this is very factorable, as it should be, into n minus 11, and then n plus 8 is equal to 0. So n is equal to 11, or n is equal to negative 8. And as before, when we run into a negative n value, we reject it. In this case, it makes practical sense because we should not have a negative 8-sided diagonal, or polygon, excuse me. So this is an 11-sided polygon. Much better than doing it by hand. So that's the end of this lesson. The next lesson will be on the Pascal's triangle, which is an interesting topic in its own, and using combinations. Thank you for your time.